Today we're going to look at the force of friction. And you might recall from our lab on Wednesday that we looked at the difference between static and kinetic friction. So this is the application that I asked you to look at. And, remember we had this 50 kilogram box here. I think that's what most people did. Friction is on halfway, like the default setting. And you can see that the surface here, you see the way that the application has it? They have the friction. The surface is rough. And if you adjust this bar, I'm not going to, but if you adjust this bar, it goes all the way down to like ice, and up here it's like, real coarse gravel. But here's what we're going to do first. We're going to push on that box and have to use this thing. So let's go with 50 newtons. And you can see that with 50 newtons of force, we have a 50 Newton force of static friction opposing our pushing force. This is Newton's third law. Back. And, you can think about Newton's third law. Your hand on the box on your hand. That's a Newton's third law application here. If you're pushing the box with 80 newtons of force, the box is pushing your hand with 80 newtons of force in the opposite direction. So we can keep going like this, and the force of static friction just keeps increasing and increasing and increasing because the base here has kind of formed a bond. I don't know if you remember from the lab, but not only is the surface rough and the force of gravity kind of bonds those surfaces together, but the electromagnetic forces between the two surfaces kind of create a temporary electromagnetic bond between the surfaces. And you have to overcome that in order to get that box to move. So the force of static friction just keeps increasing and increasing and increasing. And I don't know if you remember where we actually overcame it, but it was, I think, 126. So keep going. And then at 126, boom, all of a sudden, the box begins to move. We've overcome the force of static friction. And now the force of kinetic friction has taken over. So we treat it as two different things. The applied force is still 126. But the force of kinetic friction is less. Now, we can see we have this 32 Newton net force, and that's what's causing the acceleration. I'm going to just pause that for a second, or else the speed will go up too high. I'm going to draw a free body diagram of the situation over here. And so what we've got is, put the pencil back on, we have our box, and that is 50 kilos. Going this way, we have an applied force of 126 newtons. And going that way, we have a friction force, and the friction force is 94 newtons. Now, going down, these two forces are going to cancel, but I'm going to put them in here anyway. The force of gravity is mg, and the normal force, you might remember from our previous class, the normal force, because there are no other up and down forces acting, the normal force must also equal mg, but in the opposite direction. So the force of gravity is pressing down on the box. The surface underneath it is pressing up on the box, and those two forces, they cancel each other out. But here in the horizontal direction, we have a net force. So here we can look at the acceleration. Let's make an F net statement. And we don't need to worry about the vertical direction because there is no net force in the vertical direction. So we only have to look at this. 126 minus 94 newtons, which gives you 32 newtons, which is what you see in the equation. And then the acceleration is F net all over mass, which is 32 newtons all over 50 kilograms. And that's going to give us 32 divided by 50 is 0.64 meters per second squared. 0.64 meters per second squared. So, I'm not going to do it, but if we were to count the number of seconds it took to get up to 18.3 and divide the 18.3 by the number of seconds it took, I'm pretty sure it would come out to 0.64. I mean, this is something that you can try, but let's move on from here and see what happens when we start playing around with the force a bit more. So I'm going to Let that play. And watch what I'm going to do now. I'm going to reduce that force down. Now watch what happens to the speed. I'm reducing the speed down, sorry, the applied force down. And now I have 94 newtons of applied force and 94 newtons of friction force. You might have noticed that the 94 Newton friction force stayed constant the entire time. It doesn't matter how much harder you push now, the force of friction is a constant for that particular object and surface interface, and it doesn't change. And you can see here now that the acceleration has dropped. The acceleration has dropped to zero. The velocity is staying the same. Right now, we have uniform motion. We have a net force of zero. But here's something that students have struggled with over the years is they think that if there's no net force, that the box should stop moving. It shouldn't be moving at all. But this is an example of inertia. As long as you have balanced forces, the object will continue doing whatever it was doing before. If it's sitting still, it will continue to sit still. But if it's in uniform motion, it will continue in uniform motion until there's an unbalanced force acting on it. Now, this force of friction, and this is something that we're going to be talking about today, the force of friction has two components. Let me go back here. The force of friction is made up of two components. It is proportional to the pressure between the two surfaces. The pressure between the surfaces. So and you know this, I mean, like how hard you press the surfaces together is going to determine how much friction there is between them, right? If you relieve pressure, the friction drops. And it's easier to move things if you take pressure off the surface. And it's also proportional to the, how should I put this? It's the surface object interface. The surface object interface, and that is unique. This box and this surface have a particular amount of stickiness. And if we change the box, or if we change the surface object interface would also change. Now, the way that we quantify that is we do this. The pressure between the surfaces, this is just equal to the normal force. So this is equal to, I have to use this space here. This is the normal force. The normal force is how hard the surface is pressing up, to meet the pressure pushing down. Whatever pressure is pushing down on the surface, the normal force will match that by pushing back up. And the surface object interface is quantified by a symbol called mu. And here this is going to be mu k. Mu k is called the coefficient of friction. That's the coefficient of friction. And in this case, it's the K stands for kinetic. So it's the coefficient of kinetic friction in this case. Before the box moves, we would be dealing with the coefficient of static friction, which is higher. Now, one thing about the coefficient of friction is that the mu K and the mu S, which is the static one, they always go between 0, so less than or equal to 1. You can't have a coefficient of friction that is greater than 1, and you can't have it less than 0. So it's in some value here. So the force of friction is mu, if we're dealing with kinetic, we'll put a K there, times Fn. And that is the equation for the force of friction. Force of friction is the coefficient of friction, which is a measure of the stickiness of that particular surface object interface. It's somewhere between 0 and 1. And then you multiply that coefficient by the amount of pressure that exists between that object and the surface. And right now, the reaction of the surface, the normal force, is how you quantify that.